So this is question 6 of the 2009 paper, and we're part D and E. This is the snowboarding one. Having survived his first fall, the intrepid snowboarder makes sure his next fall is onto a surface sloping at an angle theta to the horizontal as shown. You can see the angle theta in there. It can be shown that Fr equals mg, in the brackets 1 plus h over b cos theta. And if you remember earlier, in question number 1, we derived Fr equals mg 1 plus h over b. So the cos theta is a modification to that vertical reaction force, because when it's landing straight down, it's that was Fr without the from an earlier question. It's question number 1. Question number A is part of this. But now we're interested in modifying that to produce the normal force. Okay, I'm a little bit mucky, sorry. I'm going to make mistakes today because I was up quite a bit with the child last night. Hey, they're free videos, what can you do? Anyway, quality if you pay me maybe. So we're after that proportion of it, so looking... Oh, we'll move down because I'm getting ahead of myself. Explain using physical principles the effect of the slope on the force experienced by the snowboarder. Okay, so going back to what I was saying before, we're after this one. So the Fr down the bottom is this. So this is Fr, or mg 1 plus h over b cos theta. So the hypotenuse here is your the original reaction force, which is the mg 1 plus b over h over b. Oops, I've run out of space. You know what I mean. Okay, now this is the angle required for cos theta. The only thing that remains is to show that theta is the angle that we're dealing with from our diagram here. So if I turn this into a nice little triangle here with our original mg 1 plus h over b here, and if we're after the reaction force, which is normal to the surface, because it's a force that will be experienced by the snowboarder, then the adjacent angle for the cos is this one in here, theta. And is that true? And I think we can see that that's true, because from the larger triangle, this angle here has to be 90 minus theta, because the internal angles of a triangle add up to 180 degrees, and we've obviously got the 90 degree there. So this angle here that I'm colouring in now, that has to be equal to theta. So that helps us with our cos theta, and if we take the mg, anyway, so that's deriving it. That's not actually what the question's asking us. We're actually asked to explain using physical principles the effect of the slope on the force experienced by the snowboarder. So it helps to consider the extremes. When the slope is at a 0 degree incline, the full force is experienced. Okay, so it's quite a large, the full reaction force is experienced. Theta equals 0 in this case, and cos of 0 is 1, so it's 1 times the whole force. When it's vertical, which is the other extreme, when theta equals 90 degrees, cos of 90 degrees is 0, which means there will be 0 times this part here, which means there's 0 reaction force, which makes sense, because if it's straight down, you're effectively not landing when your snowboard comes down. So there's no normal force, there's no force experienced. So I guess the slope's going to range between that horizontal and gradually down to vertical, and as the slope increases, you'll have less proportion of that force, reaction force experienced by the snowboarder. Okay, I think that covers it well enough. E. For the snowboarders approaching the ledge with a non-zero velocity, so that is, they have a horizontal velocity to start with. Okay, just remember that. So horizontal velocity, which will be constant. Remember, it's projectile motion essentially when they're going off the cliff. So horizontal ledge, non-zero velocity. The slope can be made so the reaction force, so this is the slope down the bottom, which we're working out the angle of before. The slope can be made so that the reaction force on landing is 0. Explain what shape of the slope will be required and why. Well, we did see above that if it's perfectly flat, that is theta equals 90 degrees, then there will be no reaction force. Okay, but that's just a little bit silly. So it's getting into a little bit more than that, because that's not actually landing, not improper. The principle to remember here is exactly the same, but opposite. Okay, that's not a contradiction, but of projectile motion. And the reason we have this shape for a projectile, parabolic shape, and the answer is going to be the same. It's parabolic because vertical velocity, when you consider projectile motion, say a ball that's been thrown, the vertical velocity changes, VV, changes according to the acceleration, which is g. And we have to apply basically the same but in reverse. So we're going to have a parabolic upside down, like a half pipe for snowboarding or for skateboarding, okay, which is designed to reduce the impact so you can get really, really high up in the air. Then when you come down, you gradually increase the reaction force of what's on here. But initially, which is the force on landing, you'll have zero or very close to zero. Anyway, and the reason that is because you need to have a constant force applied in reverse and constant reaction force. Hang on, my mind's just shut down. That might not be true. Okay, anyway, the answer is parabolic because it has to provide a gradually increasing force so that the person's body doesn't experience that force all of a sudden. So they want to spread out the force, increase the time as long as possible, so the deepest parabolic curve is going to be the best to spread out that impulse force and change momentum much slower, taking a longer amount of time. Anyway, so what would it actually look like? Only the first half of that drop is going to be parabolic, and then it's going to stay flat. So if you were to put this on an axis, in fact, let's change color because we can. If you were to put this on an axis with your x and your y, I know this is not a true parabola if you study your conics, conical surfaces and things, but this first half here is from the relationship y proportional to x squared, which is your parabola. The negative values of x, and then it's flat. It's supposed to be flat. You get the idea. Quite exciting, quite interesting. Yeah, covers it nicely.